Hey everybody, this is Mike Bartles from HEC. Within this video, I'm going to wrap up the Future of Flood Risk Data Initiative topic by discussing the Duwamish River pilot study in detail and providing examples of the types of probabilistic results that were produced. This video is part 4 within a series of videos devoted to the FFRD topic. In this video, I'll pick up where I left off in part 3 and discuss the various phases of study that were undertaken within the Duwamish River pilot study. Along the way, I'll provide tons of outputs for all phases. Same as last time, if you know which dam this is, please write it in the comments. Let's talk about the modeling phases that went into this pilot study and all FFRD applications. First up is the calibration phase, which begins after the HMS, ResSim, and RAS models are constructed. Within this phase, 6 historical events are used to calibrate model processes and parameters using observed data. Also, the period of record simulation is computed within this phase in order to generate representative datasets of initial model states. Observed meteorologic data without transposition is used as inputs to the hydrologic model within this phase. Next up is the conformance phase, which begins after the models have been calibrated to historic events and the period of record simulation has been completed. Within this phase, a single realization of 500 years with approximately 10 events per year is simulated. SST is used to generate the meteorologic inputs to the hydrologic model within this phase. Accurate linking between the various models is verified, and frequency-based results are calibrated using observed data. And the study finishes in the production phase, which begins after demonstration that models can achieve the standard set in the conformance phase of the project. Within this phase, 50 realizations of 2,000 years, with approximately 10 events per year, are simulated. SST is used to generate the meteorological inputs to the hydrologic model again, and a total of approximately 1 million individual events are simulated in order to generate hazard curves along with uncertainty at all locations of interest. All stream gauges with the significant period of observed data are used for calibration of the FFRD models within the calibration and conformance phases. Each of the gauges are categorized as either primary, secondary, or tertiary to describe the hierarchy for use in model calibration. More rigorous calibration metrics are used for primary gauges than for secondary or tertiary gauges. Within the Duwamish River watershed, 9 locations were identified as either primary, secondary, or tertiary locations. During the calibration phase, multiple statistical metrics are used to ascertain model performance. The metrics that are used include coefficient of determination, Nash-Sutcliffe efficiency, ratio of the root mean square error to the standard deviation, and percent bias. The upper left image shows HMS results for a single historic event, while the lower left image shows the corresponding RAS results along with their statistical metrics. Following model calibration for the 6 historical events, the hydrologic model was computed for the entire 1979 through current time period. The left and center images compare the computed and observed annual maximum series of flow for a single location. The upper right image shows the moisture deficit within a single subbasin. Now at this point, we're ready to move on to the conformance phase. Before we go any further, let's talk about compute resources. During historical event calibrations, standard desktop simulations are used to compute each model iteration. However, within the conformance and production phases, cloud compute resources are utilized to perform the actual computations. Remember, within the conformance phase, 5,000 individual events are simulated, and within the production phase, approximately 1 million individual events are simulated. In order to execute this many hydrologic, reservoir, hydraulic, and consequence model simulations within a reasonable amount of time, computations cannot be performed on a single computer. If we did that, we'd be waiting forever to get actual results. Thus, these computations are performed within the cloud, where thousands of compute nodes can be utilized to perform simulations in parallel. Now, I would be remiss if I didn't mention the terabytes of data that are generated within these types of analyses. This data needs to be accessed by multiple teammates and remote computational resources. To achieve these outcomes in a reasonable manner, all input and output data is stored within the cloud. And to navigate this treasure trove of data, a web-based application called Model Library was developed and used. During the conformance phase, the first round of computed precipitation frequency magnitudes were much larger than observed precipitation frequency. Essentially, too much precipitation was being applied to the modeling domain, which caused erroneous results in all subsequent processes. We needed to do something to correct the precipitation amounts that were being applied to the modeling domain before going any further. Now, within the Duwamish River watershed, these effects were primarily due to the heterogeneity of the terrain. Specifically within the upper portion of the watershed, orographic effects result in lots of precipitation falling from the sky, while the lower elevations receive less precipitation, typically. To account for this, a normalization raster was used when transposing each storm event. In this application, the NOAA Atlas II 1% AEP 24-hour duration map of precipitation depths was used as the normalization raster. First, the sampled storm was normalized into probability space using this raster. Second, the normalized storm was then transposed to the new location. And then finally, the normalized transposed storm was then multiplied by the normalization raster to bring it back into real space. Using this approach within the Duwamish River watershed resulted in much improved results. These images show the results of the conformance phase. The resultant annual maximum frequency curves span approximately 500 years due to the size of the specified events in the realization structure. The upper left image rehashes the precipitation frequency results by comparing the SST outputs against observed data for numerous durations. The middle image shows flow frequency results computed by HMS against observed data. This right image shows stage frequency results computed by RAS against observed data. At this point, we are ready to move on to the production phase. Within the production phase, approximately 1 million individual events are simulated within HMS, ResSim, and RAS. The resultant annual maximum frequency curves span approximately 2,000 years due to the size of the specified events and realization structure. Like I said before, we like to call these spaghetti plots. Each realization produces a frequency curve, shown in blue, and when they're all plotted together, there are lines all over the place. However, we can compute mean, median, and confidence limits around these observations, as shown by the red curves, and we're nearly there. Finally, we can also compute depth and consequence frequency at every single structure within the watershed with uncertainty, which is so cool. This image demonstrates those types of outputs for a small area. Keep in mind that the inundation results shown here were gathered from multiple events. There isn't a single simulation or event that represents the 1 in 100 AEP conditions everywhere. But we can visualize AEP-specific depth grids by sampling from the multitude of results that we generate. In review of this entire series of lectures, FEMA's FFRD initiative is attempting to produce a more risk-informed national flood insurance program. FFRD is pioneering the transition from binary to probabilistic assessments that depict hazards in a graduated manner. In support of FFRD, the U.S. Army Corps of Engineers is collaborating with FEMA to provide methodology recommendations. An SST is foundational to FFRD and produces a variety of storm events that fall over a watershed in any given year, and any of those storm events can produce floods of interest. 3 pilot studies are being undertaken to provide standard operating procedures for model construction and simulation. And I spent a lot of time talking about the Duwamish River pilot study in particular, and showed how this pilot study improved the FFRD SOP and produced graduated estimates of flood hazards and risks. Now, thanks for watching this entire series of videos, and I'll see you in the next one.